meat of the course, which is the probability tools. We will use them throughout this series and they are really, really important. So the first one is union bound, which is pretty simple. Probability of event A union probability of event A union B is less than probability of A plus probability of B. This is just like saying A union B is equal to A plus B minus A intersection B. Both of these sides, like, that's the main core idea if you look in the Venn diagram set theoretical way. So if probability x greater than epsilon is less than some f of e, then we want to say with probability 1 minus delta, at least 1 minus delta, x is less than some other number. So probability x is greater than epsilon is less than f of e. That means probability x less than epsilon is greater than 1 minus f of e. If I make f of e as delta, that means epsilon is f inverse delta. So with probability greater than 1 minus delta, so probability at least 1 minus delta, x is less than epsilon. So x is less than f inverse delta. If you write it in paper, it's pretty convenient. The Jensen's inequality is if f is convex, then f of expectation of x is less than expectation of f of x. Why does this hold? We'll look at a diagram. Let's say we only had binary, whatever, x and y, with the probability p of being x and probability 1 minus t of being y. So expectation of the variable x is t times x plus 1 minus t times y, which is this. Now if I evaluate f outside the expectation, because of it, the nature of the function being convex, we see that this is below this line. And what is this line? This line is the expectation outside the f of x. So we connect f of x and f of y, and we take probability p times f of x and probability q times f of y. So we get this variable, this point. And as you can see that the expectation outside a convex function is greater than the expectation inside a convex function. This comes from the definition of convexity, and that's it. That's the Jensen's inequality. It's going to be useful because we are trying to make sure all of our loss functions are convex. And that way we can use convex optimization and Jensen's inequality. The next one is an interesting one. The expectation. If x is positive, then expectation of x is just the tail probabilities, in the sum of the tail probabilities. And I asked ChatGPT for this one, and here's the proof. We write expectation of x as x f of x, right? Integral f of x f of x, that's the basic definition. So now for any x greater than 0, I can write x as equal to the indicator variable integrated from 0 to x. Like just one, sorry, not indicator, just one. This constant function integrated from 0 to x, that's x. If I put that inside the expectation, I get this particular this formula. Now what I can do is swap the integrals, that is take 0 to x outside and then take infinity inside. What we get is that what we instead write is that 0 to x and then integrate from 0 to infinity 1 dt f of x dx. Instead we write it as x going from t to infinity and t going from 0 to infinity. fx dx dt. This is the Fibini's theorem. We interchange x and t integrals. And now this is just basically this interior is just probability that x is greater than t, and this is just the integral over all t going from 0 to infinity. Like if you see Fibini's theorem, this is just an application of Fibini's theorem, that's it. I mean, I don't have intuition behind it, but apparently ChatGPT does. So think of the complementary CDF as the probability that is literally the area under the tail probability curve. Yeah, I suppose it works. I suppose Fibini's theorem works, and this is it. So, I mean, just remember it, I suppose. That's all I can say about this. Markov's inequality is when x is positive and epsilon is positive, the probability that an x is greater than epsilon is less than expectation x divided by epsilon. Why? Let's look at this. Let x be a non-negative random variable, then probability x is greater than epsilon is less than expectation divided by epsilon, right? And expectation divided by this epsilon is just 1 over t. So this is the right way of writing this. It's the same thing. Epsilon here is t times expectation of x. So this is the right way of writing this. How is this true? Probability x is greater than this particular number is probability that x is equal to some number x, and this sum over all x is greater than. So basically this is just an integral. This is just an integral over x greater than this number. Now because x is always greater than this number, we can multiply with x divided by t times that number. We can multiply by x and that number, divide by that number, and it will always be greater than 1 as everything is positive. So we can write this inequality. And now if you look at this is just now this will always be less than if instead I did it on the entire x, because what I'm trying to do here is trying to write this as an expectation, because I can see that there is a probability x equals to something and then multiplied with something. So I'm trying to write it as an expectation. To write it as an expectation, I want to take it over the entire domain of the random variable. So I expand the domain and I can only go higher because x is always positive. So this inequality holds, and this then is the expectation of x divided by t, this epsilon number. And this again is just expectation of x, like this is a constant. So it comes out and you get 1 over t. So this is Markov's inequality. It's pretty, you remember it, it's going to be easy. That x is greater than epsilon is less than this number. And now Chebyshev's inequality is just the same thing applied to x minus epsilon x whole square. So as you can see that it could be any x now, and x minus epsilon x, the whole square will always be positive, and that positive number is greater than epsilon, which with probability at least expectation of that square number, which is again sigma square, divided by epsilon square. So we are doing this on squares. Basically Chebyshev's inequality is the Markov's inequality applied to this terms squared essentially. The Hoeffding's inequality is the main one which we are going to use, and I don't think there is a proof for it, but it comes from Chebyshev's inequality and the Chernoff bounds. What the idea is that if my x's were independent random variables in some a to b domain with the same expectation and whatever, like a to b domain, then for any epsilon greater than 0, this inequality hold. Mu is the real mean, and 1 over m, the sum of this is like the empirical mean. So what they're trying to say that is that the empirical mean is deviating from the real mean with more than epsilon. It can only be less than exponential minus 2m epsilon square over b minus a the whole square. Basically, your empirical mean deviates from your true mean by greater than epsilon. Like epsilon it goes farther than your threshold with some probability which is very less, which is exponential, like exponentially small. If you have a large number of m, if you increase your m, like the number of samples you have, this exponential decreases quite rapidly because it's exponential. And that makes sense because the more m you have, the closer you're going to be to mu, right? That's the law of large numbers. If you take independent random variables and take their average, you're going to be really close to your real mean. And essentially that's what this side is saying too. This side is saying, this inequality is saying the same thing but from the positive side, like it goes higher than mu by epsilon with the same like exponential decay, and this one is saying it's lower than mu with the same exponential decay. We can put a modulus and something like this. We can put the modulus and add these two terms together. It would be the union bound essentially. And then McDiarmid's inequality is something which is even more general. So let x1 to xm be independent random variables taking values in some u, and then the function, there is a function which is going from this m dimensional input to r. So this function in this case is just this mean function which takes everything, sums it up and divides it with m. Now what it is saying is that if this function has this quality, that if I only change one point xi to some xi prime, which I sample again from this distribution, and if the function value changes with not more than ci, let's think about it. If what is this trying to say is, if I change one input and my function value changes only slightly, some ci, some small number ci, that means my function is pretty robust, so to speak, that I could change my input variables and it wouldn't change too much. Then for all epsilon, this function on random variables minus its expectation on those random, like this expectation of the function on the random variable can be greater than epsilon with no more than exponential decay in the ci square. If you look at this inequality and you look at Hoeffding's inequality, what you really find out is that if my xi was taking values in ba, then I change a value of xi, it could only change with no more than b minus a divided by m, because it could either be b and I change it to a, and then mean changes by no more than b minus a over m, because I am dividing with this m. So here ci is actually b minus a over m, right? So ci square is b minus a square over m square, and it is same for all of these xi's, and summing over all m's, the m square m cancels and you get an m in the numerator. So if I were to use McDiarmid's inequality with the function which is just the mean function, I get that ci square is b minus a square over m square, and this becomes 2me square over b minus a square, like if I take the sum, and that's indeed what we see here, b minus a square over m square multiplied some m times, so it's just an m. So essentially it's the same. So the McDiarmid's inequality is the more general version of Hoeffding's inequality, and it's the one which is more important. So if you verify this, that every function, if you change its ith input to some xi prime, anything, the maximum it can change is ci, no more than that. That means it's pretty robust up to the tolerance of ci. That means this function minus this expectation of the function over all random variables m can only be greater than epsilon with some probability which is exponentially decaying in epsilon square. Markov's inequality, Chebyshev's inequality, let's look at the proof, I guess. So Chebyshev's inequality is just this thing applied to the square, and the results follows from the Markov's inequality. This you can pause the video and ponder, it would be pretty simple. Law of large numbers is pretty cool, not bad. Again, this is like saying that if I keep increasing my sample, I am going to converge to the mean almost surely, and it can come from Chebyshev's inequality, or it can come from, let's say, Hoeffding's inequality. It doesn't matter. So there is Chernoff bounds, and there is Chernoff bounds which we have not looked at, but this is again another corollary. What is this? Is that if my hypotheses were to take values in 0, 1, then my risk can only differ by 1, right? So b minus a is 1 in the Hoeffding's inequality, and you put b minus a as equals to 1 and you get this particular thing. This is only for 0, 1 loss though. This is Chernoff's bound. Chernoff's bound, you can look it up. It's fine. And Jensen's inequality. So we are good. Basically, remember these two things. These are the really important things. Jensen's inequality is important, and all of these are important, and Hoeffding's inequality and McDiarmid inequality is important. Even if you don't get them now, we will use them so often, again and again, that it will just become second nature by the end of these videos. So that is slides 1, and we will do slides 2 next time.